Hello and greetings to you all. My apologies for all the Zoom screw-ups we've been experiencing. So I'm just recording this session alone, and with the sincere hope that each and every one of you can later on tune in and pick up the recording and hear it. It'll be saved as a YouTube, and I will save it in Blackboard, and I'll show you rather quite exactly where I will be doing that. This is your Real Ear course, and each week we plan to meet at 11:30 Wednesdays Central Standard Time. We tried to do that yesterday. It didn't work because I couldn't record a darn thing. So I've been on the horn constantly with OTC's IT help, and finally we're slowly beginning to figure ourselves out. At any rate, we all learn as we go, and I thank you for your patience in dealing with me. Here's hoping we have a great course this semester. Real ear measurement. I'm going to go over the pieces and parts and parcels of it. It follows on the heels of fitting methods. Real ear and fitting methods developed together. Fitting methods evolved before real ear came into the picture in the late 1980s. Okay, and then real ear entered the scene, and both of them seem to evolve or rotate around each other. Their development is completely intertwined. Okay, so when you teach fitting methods, you almost necessarily stumble into real ear. And when you're teaching real ear, you won't necessarily stumble into fitting methods. So it's good you've had 150 fitting methods, and we are going to actually, in this course, cover fitting methods again. Okay, we'll just do it quickly. We won't spend the whole semester on it, but we won't get to the actual nuts and bolts of real ear measurement until a few weeks from now. There's a few things that I think we really need to have our ducks in a row. We really need to basically have our act together when it comes to ANSI testing, fitting methods. Okay, these two things really important, and also a little bit about venting, ear molds, filtering, a little bit of acoustics when it comes to hearing aids. So I'm going to cover just looking a little bit at that as well. So in the first, I think what we'll cover with a little bit of today, we'll look at non-electronic modifications of hearing aids. Non-electronic, okay, just mostly vents in ear molds, whys and wherefores of occlusion effect. Next week we'll cover ANSI testing quickly, just do it for a week, and then we'll get into fitting methods and we'll review that, and then we'll get into the old way of doing real ear, how real ear began. And then after that, we'll talk about the way we do real ear today. And we'll talk about issues of doing real ears with receiver in canal hearing aids and things like that. So it's a broad scope of things that we're covering in this course. Of course, you will have a couple of labs as well concerning real ear. And we'll be talking about that as well as the time comes, okay? For now, what I want to do is share my screen with you and go into Blackboard and show you where we are and what we've got here, okay? I'm going to choose my desktop here, share screen, and I think what I'm going to try and do here is go to good old my OTC, and I'll go log into Blackboard here, and I'll work my way down the page till we get all the way down to 250, and I'll pull up into real ear measurement. And you will therefore see on the left-hand side, you'll see lessons. Your quizzes, by the way, will be put into Dropbox. Let's talk about quizzes. You're going to get a quiz every week in this course, okay? There's a quiz, it's just a 10-question quiz. There's 10 of them throughout the semester. So some of the weeks you won't have them, but there's 10 little quizzes. throughout that are sprinkled all over this particular course, okay? And in fact, I think the first quiz is actually on today's material. So, but it's easy peasy Japanesey, don't worry about it. At any rate, your quizzes will be put into Dropbox. Your lessons, of course, are much the same as what you may have encountered in previous courses if you had with me. They're always in units. And so you'll see today's unit, non-electronic acoustic modifications. And in that, you're going to see introduction to course, reading assignment, blah, 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 but lecture materials. If you click on that puppy, you're going to see 4 things. But really, 2 of them are of the most importance, the notes and the PowerPoint. And if you look at the notes, I'll just pull mine up here. That's what they look like, okay? Good old acoustic, non-electronic acoustic modifications. And always have these notes printed up before class, okay? So just have these. These are your cheat sheet. And 100% of your quiz material comes from this, okay? From these notes. They also come from the accompanying PowerPoint that comes with it. So there's always the notes and the corresponding PowerPoint that goes with it. Very important to always keep that in mind. And then this ear molds thing, that's just something that Ms. Royer had supplied. And then this PDF is simply a PDF of these notes. So that's just extra. But always look for the word notes and PowerPoint. You can print up either of these. If you print up the PowerPoint, you can print it up as 6 slides per page, 3 slides per page, whatever you feel like, okay? And the notes are there for you, but that's what I lecture from each and every week. So then after this first unit, we're going to start going into ANSI testing, and we'll start looking at that. And you will see that lessons here, under lessons, I'm going to pull back to it, you'll see those are grayed out. And I guess that's because Lynn Royer has not yet freed those from release to you yet. We're covering this top one here in gold, okay? So when you're looking at Unit 2, you'll see it grayed out. Unit 3, fitting methods reviewed. See that? Unit 4, real ear measurement. And it's early real ear measurement. Always divide fitting methods that way too. There's the early methods and today's methods. Same with real ear. There's yesterday's real ear, today's real ear. Back to fitting methods. Hearing aid fitting methods based on linear hearing aids. And then real ear entered the picture. And then we did fitting methods using compression hearing aids. And yesterday's real ear was always real ear, unaided response. And then they put the probe in, real ear, unaided response. And then they put the probe in and they put the hearing aid on top of the probe, real ear, aided response. And then real ear, aided response minus real ear, unaided response gave you real ear insertion gain. That's yesterday's way of doing real ear. We don't do it like that anymore. Today, you put the probe in the ear right away, you put the probe in the ear, and you put the hearing aid on top of it. So you're not even looking at REUR, open, unaided ear canal resonance. We don't really do that very much, okay? Today, we do what's called speech mapping. And the audiogram is displayed on the monitor, and then you can see how unaided speech, what it looks like across the guy's hearing loss. And then you can see what the aided speech looked like. Perfect visual tool for counseling. So today's real ear is a totally different kettle of fish from early real ear, okay? And then we'll get into Unit 6, manufacturers talk, real ear measurement walks. Manufacturer software is always meant to get you in the ballpark with the hearing aid, okay? It'll set the hearing aid up according to the guy's hearing loss. No problem, it'll help, okay? It gets you in the ballpark. But real ear measurement actually shows you what you're really getting. So the software predicts and gets you near to where you've got to go? Are you hitting the target of the fitting method? Because when you're doing real ear, you're choosing a fitting method right away. And is your hearing aid giving you the proper output? Are you hitting the target properly? And the software will usually paint a beautiful rosy picture saying, oh yeah, for sure. But actually not quite true, okay? You're not really there. So fitting software predicts and gets you in the ballpark. Real ear verifies. Verily, verily, I say unto thee, did you really hit the target? Are you there or not? The software says you're there, but are you really there? That's the purpose of real ear measurement. Okay, so that's what I wanted to show you, the lessons, the things that we're going through. And then there's a unit on patient care and counseling, but I don't think that's really too much of a unit here as really. And unit 8, review for final exam, mañana, later, another day. So basically, non-electronic acoustic modifications, ANSI, fitting methods, early real ear, today's real ear. That's essentially where we're going. Then you'll see this box here called Zoom Lectures, of course, and this is where your meetings are. And I had a lot of trouble even today when I went to this session. When I first pulled it up, it wouldn't let me record. So even on day 2, today, Thursday, at 1:15, I'm on the phone to OTC to help me get it to record. So it is finally recording. We are, hallelujah, finally recording. So I'll stop share for a second here so you can see my ugly mug again. And see, normally if we were all attending, and it's not your fault, it's because the session didn't get off correctly, but if we were all attending, we could be shooting the breeze with each other and talking, and that's what I'm hoping can happen next week. We can have a bit of a chit-chat and get to know each other again, okay? Anyway, what I need to do once this session is all done is save it to a YouTube. Okay, save it to a YouTube, and then what I'll end up doing, I'll share screen again here. I'll save it to a YouTube, and I'm sharing my desktop here. And once the Zoom session is recorded, see, today's Zoom session was January 26th. Today, 1 p.m., which we already blew that one, but I'm doing it now. And then from now on, you'll be looking at Zoom sessions February 1 and forward. So that's next week, Wednesday at 11:30 and going on. And I want to say we'll always use the same link, same ding-dong link, no problem, okay? So then any Zoom session from now on, this is the one, this is where you want to go. So you'll go under Zoom Lectures, and then you'll hit, you'll hit the Zoom sessions and things like that. Now let me click back to Zoom Lectures again. There you go. So you come into Zoom Lectures. This is your meeting invitation. In this one here was your meeting invitation where you had today's thing and the ones going forward, correct? Okay. And when you want to hear a recorded session, you'll go under Zoom Recordings. Okay, and then here's just a test one done by Lynn Royer. This isn't anything, okay, but the recording is where is stored in this folder. So when you go, that's where your Zoom recording, your invitations in this folder, your recordings here. Okay, get it, got it, great. Yeah, I'll talk in my best British from now on, eh? Quite. I guess President Trump's first visitor to the United States is, I guess, the Prime Minister of England. I guess she's coming by today or something like that. So I've heard. Anyway, now, let's just show you, we'll start our today's talk. And I'll gab for about 30 minutes and then we'll bag it, okay? So you can see my weird the little box over here. We're sharing screen. We're looking at non-electronic acoustic modifications. And what does it say there? And you will always, again, I'll remind you, always print up the session that you're going to be attending. I mean, how would you know today? Most of you didn't print this up because how would you know? But from now on, like with next week's, print up ANSI, Unit 2. Make sure you print that puppy up. And then I will talk through it and you can follow through with your very same notes. Non-electronic acoustic modifications. It's a lost art. Most hearing aids today are digital, which allows for an amazing amount of frequency shaping. But non-electronic acoustic modifications are techniques when used to fitting quite inflexible analog hearing aids, but they still have an art today. They help shape frequency responses, and any good HIS should have a handle on them. Besides, it's cheap. Now, your ear canal cylinder, just like you learned in acoustics, it's a quarter wave resonator. Your ear canal, you're going to be looking down a lot of these when you're doing real ear, I can tell you that, okay? You're going to get to know the ear canal really well because you're always doing otoscopy every time you're doing real ear. You always look in the ear first. Is it clear? Is there too much wax in the ear? Can I properly insert the real ear probe tube into the ear close to the drum? And you always have to look in the ear ahead of time. Anyway, your external auditory meatus, or ear canal, is about 2.5 centimeters long, 2.3 to be exact. It resonates best with sound waves that are about 10 centimeters long. And if you look at your acoustics notes, frequency is the speed of sound over the wavelength. Wavelength is speed of sound over the frequency. These are just simple little things, but if you do, frequency equals speed of sound, 340 meters per second, divided by 9.2, okay? You're going to end up with 3,800 hertz. So that's what your ear canal, it's a quarter wave resonator. In English, that means it's a cylinder closed at one end, namely your eardrum. It's a cylinder open at your ear canal opening and closed at the other end, just like a cup, okay? Here's my good old cup. It's a cylinder and it's a quarter wave resonator, closed at one end, open at the other. And so your ear canal would naturally vibrate or resonate best at 3,800 hertz. But your ear canal is also made out of flesh and bone. And so it's not made out of steel and glass. And so yes, it's going to resonate at a more of a spread of frequencies. And it's going to resonate basically between, now remember this, between 1,500 hertz and 4,000 hertz. And it's going to give about 20 decibels to that. I'm wondering if I have a picture of it. I don't, and I really ought to have that picture, but we will in future classes. I will be showing you good old outer ear canal resonance. We don't really have it here, although I might be able to just pull up something and show it to you, just in a different class or something just different here. Let me try this just for fun. Okay, just for fun. Cheers with me. This is a nice thing about doing a good old Zoom session. We can kind of play. So I'm going over here to my PowerPoints, and I'm going over here, and I'm just going to pull up a thing that we commonly do. Okay, I'm going to pull up this guy here just to show you a PowerPoint slide of that good old outer ear canal resonance. And there it is. Okay, so here's your outer ear canal resonance. Here's an audiogram with speech sounds. Look at where your outer ear canal resonance is, between 1,500 hertz and 4,000 hertz. Why? Because your ear canal is a quarter wave resonator, as we have described. Okay? So essentially, that's kind of the nice thing about being able to share this screen stuff with you. Okay, so the ear canal is made out of flesh and bone, so the resonance is spread out a bit, so the exact frequencies are fudged a bit. Always remember this, the peak ear canal resonance is 2,700 hertz in the average adult. So the peak resonance, this peak right here, would be about 2,700 hertz. Okay? That's something else to always keep in mind. So, hearing aid, when you put a hearing aid in, you've plugged up the ear. And now you've destroyed this natural key of listening. So a hearing aid has to restore this lost resonance and also make up for the hearing loss. 2 to 4,000 hertz are also very important for understanding speech, and some ear molds don't allow enough highs to get into an ear. So for high power BTEs, beware of narrow tubing, because narrow tubing is an enemy against highs, and we'll discover why that is. In fact, I can even describe it to you now while we're on the topic, just so you know this, okay? So I'm going to stop sharing for a second here, and I'm making a tube. Here's a horn, okay? If I talk into the wide end and let you get the sound through the narrow end, you're not hearing my high frequencies very well. You see that, or you hear that? Okay, but wider tubing, if I speak into the wider end, now you're hearing the high frequencies of my voice much better. You see? So narrow tubing in a high power BTE, you should, as a clinician, you should say, you got to replace that because you're blocking up too much of your highs. You see what I'm saying? So non-electronic acoustic modifications. Okay, enough on that. Ear mold types and material. The most common by far is lucite. And the most common style used to be a skeleton. I'm wondering if I have a picture of that, sort of, kind of, but not really. But ear mold, let's see if I can show you a kind of a picture here. Here's an ear mold stuck in someone's ear or whatever, but it's a solid ear mold. We're talking a bit of a vent over there, okay? Let's go back over to, where were we now? Here, okay? So what I'm going to do is I'm going to share screen here again and show you some of what I'm talking about here. Okay, share screen. So we'll go up. We'll go up higher into this PowerPoint here. Okay. So here's the spectrum of speech. And you can see that there's more energy in the low frequencies of speech, and it drops off in the high frequencies, right? Average speech is about 65 dB SPL, spoken at about a 1 yard distance. Here's the spectrum of speech. Low frequency vowels, louder and lower, high frequency consonants over there. Here's speech sounds on an audiogram. Okay, when you looked over here, it went down, and that's because the decibels were plotted up. When you're looking at an audiogram, the decibels go greater going down. So here's the spectrum of speech across an audiogram. It just happens in the reverse. Vowels are loudest and lowest. High frequency consonants are the softest. Anyway, when taking ear mold impressions, as you've likely done quite a bit by now, you're inserting the foam block into the canal. You're looking at the impression to make sure you've got that impression correctly. Here's a correct, accurate impression. This picture is showing you poor ones. Always realize that the ear canal has two bends. Okay, an initial bend here and then a second bend over there. Always realize that. That's why when you're looking at an ear canal, you'll pull the ear up and back, and that straightens out the dog leg of the ear canal. Anyway, what we were saying in our notes earlier, blocking up a canal with a hearing aid destroys that natural resonance, right? So here's an open ear canal. There's that outer ear canal resonance. There it is. We hear it like this on the right, no problem. It just sounds fine, okay? Now you're blocking that ear canal with a hearing aid or a mold. And so if this is the frequency response of the hearing aid, actually it's going to really look like this on the right because you've blocked off that natural resonance. Okay, and when you've blocked off that actual resonance, what the hearing aid you see doing, you're going to lose a bit of that. So hearing aids have to make up for that lost resonance, plus provide gain for the hearing loss. Now, here are 3 non-electronic acoustic modifications: venting, damping or filtering, and horns. Well, horns is what I talked to you with this piece of paper here, okay? Horns are when I opened up that thing or turned it reverse. But let's move on here or we'll never get done, okay? Here's the 3 modifications: venting on the left, filters here, horns here. Okay, and remember, we're talking old hearing aids or BTEs that use number 13 tubing. We're really not talking RICs here very much, except when it comes to venting. Okay, venting especially is the most important non-acoustic modification, non-electronic modification. And venting comes with selective vents. You can open the hole, make the hole larger or smaller by plugging, here's the vent. Okay, the sound comes through your number 13 tubing from the hearing aid, and your vent is this hole in the ear mold that goes parallel to the number 13 sound tube. Okay, and then you could adjust the size of the vent by plugging it with what they call the selective vent. So when we're looking at what we're reading here, okay, here we go. I know we mentioned ear mold types and materials. Lucite skeleton is by far the most common for adults with BTEs. Softer materials for kids. Also, softer material is often called silicone, and it usually totally blocks up the ear. If you see someone's mold and it totally covers up the concha, you know that guy's got a whopper of a hearing loss. Okay? The smaller the mold, usually the less the hearing loss. Now, RICs are a little bit of a different situation, receiver in canals. They have domes, you know, that just plug into the ear. But those domes often have huge vents. Now, read with me here. General frequencies of ear mold acoustics: venting, damping or filtering, or horns, okay? Venting controls the lows. Damping or filtering is mostly the mids. Horns affects the highs. Horns and filters were relied upon heavily in yesterday's analog hearing aids, not so much in today's digital hearing aids. There's a tension between vents, horns, and feedback. Horns increase the highs, but if your vent is too large, the highs are going to leak out of the vent and you're going to get feedback. Okay, so there's always a bit of a tension that way, but let's look at venting closely. It's a short, wide hole in the ear mold done to reduce low frequency amplification. What happens here? Well, with the vent, let's go up a slide. When you have a vent, you are allowing air inside your ear canal, to communicate, follow my cursor, with air outside. So you've increased the acoustic mass of air. And low frequencies resonate with mass, don't they? Highs resonate with stiffness. Well, if you've increased your acoustic air volume because you've made outside air communicate with inside air because of a vent, the lows are going to follow that, like Hansel and Gretel following the crumbs of bread to find their way out of the forest. So read with me here. Venting allows the lows to escape out. It allows the low frequencies in your ear canal to get out. And what produces a lot of low frequencies? Your own voice while you talk. Plug your ear, and go ahead and talk. The ear that's plugged is going to hear your voice louder, right? Plug this ear and talk. You're going to hear yourself louder in the ear that's plugged. If you don't, you've got a conductive hearing loss. It's called the occlusion effect. Venting reduces the occlusion effect, especially for those who have good low frequency hearing and for those who have high frequency hearing loss. So for sloping losses, venting is very important. Selective vent for BTEs or ITEs was this slide here. Okay, I just showed you that. And that's just done by trial and error. And remember, these are not really with RICs. This is not with receiver in canals. You can choose domes that have wider vents or smaller vents. That's today's lingo. Okay, but the principle remains the same. The bigger the vent, the more the lows go out. Back to your writing here. Don't worry about parallel and diagonal, who cares? No, don't even worry about that. What are big vents and what are small vents? Memorize this. Big vents, 4 millimeters wide in diameter. That's a big vent. Now, what's a millimeter? Well, a fingernail, let's see if I can, here's a fingernail. A fingernail is about 1 centimeter wide. How many millimeters in a centimeter? 10. Whoops, here, all 10. So 4/10 as wide as my fingernail. So if you divided my fingernail into 10 slices, 4 of them is the biggest vent you can have. 0.8 is slightly less than 1 millimeter. Those are tiny. Those are called pressure vents. A pressure vent is a small vent, not really meant to affect the acoustic response. It's just meant for physical comfort in your ear canal. So that, when you push in the hearing aid, you're not pushing the eardrum in, but because of air pressure. And when you're taking out the hearing aid, you're not sucking out your middle ear, your eardrum and middle ear ossicles by going poof. It just allows more comfort that way. Okay, so venting, occlusion effect. Memorize that, okay? For whom it's intended. Who gets the occlusion effect? Anybody with normal hearing and anybody with sensory neural loss who has good hearing in the low frequencies. The bigger the vent, the more the lows escape out. So to show you here, just in a picture, because I think it's always very valuable to look at this stuff, the bigger the vent, here's a small 1 millimeter vent, okay? Here, closed ear mold. Lows aren't getting out. Little vent, a little bit of lows come out. The bigger and bigger the vent, the more the lows get out. Do you see that? Influence of vent diameter on the occlusion effect. And the effect of venting is mostly below 1,000 hertz. Here's another picture showing you the same thing, okay? Tiny vent, bigger, bigger, and bigger. And the larger the vent, the more the lows escape. And what are the vent sizes? From 0.8 millimeters to 4 millimeters. And receiver in canal hearing aids can allow very large venting on the dome. Okay, now let's look at the second non-electronic modification, and it was called filtering. Filtering is tiny little screens. Look at these tiny little screens. And the tighter the screen, the more the filtering. And what did those screens do? And they were put in the ear hook of a BTE. So you have the ear hook, the BTE hanging around the ear, and they were in the hook that hung on top of the ear, and you put your tubing onto that hook, and then your tubing goes into your ear mold, right? So you have your BTE, the ear hook, the number 13 tubing, and the ear mold. And the filters were usually located in the ear hook. And what they did was they affected, all hearing aids have plumbing in them. Okay, they've got wires and tubes and stuff inside, and the stuff resonates. And in all hearing aids, you get generally 5 general peaks of resonance. This is the frequency response of a hearing aid, of some typical generic hearing aid. And what filters do is they dampen the peaks in a frequency response wherever they may be. Filters cause resistance. Now, remember from your acoustics, we talked about resonance, the favorite vibrating frequency of an object. And remember in acoustics, here, I'll stop sharing for a second. And you'll just have to look at my ugly mug here for a second, okay? And we said that mass resonates with lows, stiffness resonates with highs. And we said if you take the smile of resonance and flip it upside down to a frown, you've got impedance, the blockage of sound. Mass opposes high frequencies. Let's face it, a locomotive of a train does not want to be jiggled very fast. You can't. It's too heavy, okay? Whereas stiffness, like a tight spring, it's hard to push a tight spring slowly and pull it slowly, but it's easier to go yeah with a tight spring. You see, stiffness resonates with highs. Stiffness opposes lows and resonates with highs. Mass opposes highs and resonates with lows, right? Those are two aspects of impedance. The third one is called resistance. And any object that transmits sound also gives resistance. And resistance is like simple friction. It's going to be the same in any object for all frequencies. And that's exactly what filters do. Filters dampen the peaks. Filters, these tiny little screens in a hearing aid. Where am I now? Filters, down to, there you go, filters. Tiny little screens dampen the peaks of hearing aids wherever those peaks may be. So now we've covered our second acoustic modification. Venting is the kingpin though, okay? All right, don't worry about some of the details in here, different filter colors and lamb's wool. All of this stuff is junk. Most people, we don't use it anymore, except high power BTEs with number 13 tubing. They might use filters, okay? But most receiver in canal hearing aids and thin tube hearing aids and, you know, all these, they don't use filters anymore. Same with horns. Horns, a flaring. Remember, like the tube that I made for you. Okay, that tube. All right, this ugly thing. A flaring of the. Well, I'm going to show you again. We'll just get a picture of it. Okay, when your tubing gets wider, you're going to increase the highs. That's me talking into the skinny end of the tube. But the one on the right is a reverse horn. Now I'm talking into the wide end of the tube, okay? So horns used to be, look at the ear mold. Here's number 13 tubing. The bigger the horn, the more the highs. The smaller the horn, the less the highs. If it stayed straight through like this middle one, you had the frequency response that was whatever. But if you made the tube narrower, you cut off the highs. If you widen and flare it a little bit, you increase the highs. Okay? So these are just pieces showing you. Now here's thin tubes in thin tube hearing aids. Now I don't mean receiver in canals. The BTEs of today that are usually cheaper than receiver in canals. They have a thin tube. They don't have the wire going from the amplifier of the hearing aid to the receiver that's in the canal. The receiver is in the hearing aid yet, and the sound is being delivered through the tube. Okay? They look the same as Rick's, but they're cheaper. Anyway, when you've got a regular tubing number 13, when you're using those thin tubes, you're cutting off the highs. So guess what? The manufacturers had realized that, and they make the amplifier, therefore, deliver more high frequency amplification to counteract for this. Okay? But just as clinicians, you should be aware of that. We'll go back to the picture here and finish for today. Okay, so here you go. Tubing, most common tubing is number 13 tubing, 2 millimeters in diameter. That'll be on your quiz. Bet you dollars to donuts. Okay, thin tube BTEs, like we just talked about, their internal diameter, look what it says on the bottom, less than a millimeter. Okay, so slightly less than half the diameter of regular number 13 tubing used for higher power BTEs. The biggest, though, the horn effect isn't really used that much anymore because today's hearing aids are digital and they're very, very flexible. But today was just meant to give you kind of an overview of non-electronic acoustic modifications. And the most important one for your consideration is venting. Okay, and we started out today's talk by talking a little bit about what happens when you've got good old the ear canal as a what do you call it, as a quarter wave resonator, and the fact that that's being blocked off regarding speech. Okay, so these things are important to realize. Let me just hit the old home key, see if I can get you there. There, speech spectrum drops off in the highs. Okay, and an audiogram that goes the opposite way. You don't want to cut off the highs in a hearing aid, so you have to make sure that you appreciate what you're doing. When you plug up an ear, you're losing that natural outer ear canal resonance as shown here. Okay? Acoustic modifications are meant to deal with that. But the biggest one we're worried about is venting with the occlusion effect. And what's the biggest vent? 4 millimeters. Domes that fit onto receiver in canal hearing aids can be as wide as have holes as wide as 4 millimeters, or you can elect to choose smaller holes in the dome that fits onto the RIC receiver. Okay, you can elect to do that too if you don't want as much venting, because maybe you're letting out too much lows. It's been a slice. I'm going to stop here. I'm going to stop sharing my screen here, and I'm going to stop recording. Then I'm going to upload this as a YouTube and hope and pray that it all works. I'll stay in touch with you for sure. My apologies again for the screw-ups taking place at the beginning of the semester, but yeah, I guess it's how we all learn. Anyway, thanks a lot, and adios to you all, okay? Pause recording. Yeah.